about a new family of sigma models which have as a target space Jacobi manifolds. This is based on a work in collaboration with Francesco Vascone and Franco Pezzella. Okay, so this is the outline of my talk. I will give some motivations. Then I will review the Poisson sigma model, which is the one that we want to generalize. Exactly going from Poisson manifolds to Jacobi manifolds. Then I will introduce the action for the Jacobi sigma model, and I will work out an explicit example, which is the case where the target space is the manifold of SU2, which is a contact manifold, and then a special case of a Jacobi space. And then I will summarize. So, motivations, as I said, the main is that it is a natural generalization of the Poisson sigma model. And analogously to the Poisson sigma model, it may bring to deformation quantization of Jacobi manifolds. So it is known that the Poisson sigma model has been used by Cattaneo and Felder to prove the deformation quantization formula by Kontsevich. So possibility would be to explore a similar model for manifolds which have a Jacobi bracket instead than a Poisson one. Jacobi manifolds have some special cases which are contact and locally conformally symplectic LCS manifolds, which are the two main cases of Jacobi manifolds, which include Poisson symplectic and globally conformally symplectic as special cases. It can be shown to be gauge invariant with an interesting algebra of gauge generators. In its basic formulation, it is a topological field theory, although it can be made dynamical, and it may contain a two-form field, which is neither exact nor closed in some cases at least. So it is a West-Zumino with a like term. And then it may describe new backgrounds for string dynamics. So briefly, let me review what is the Poisson sigma model. It is a two-dimensional topological field theory which was introduced in the 90s independently from Ikeda and then Schaller and Strobel, which has as a target space a Poisson manifold M. Pi is the Poisson tensor field. The action looks like that, with X, the usual embedding manifold map from two-dimensional sigma to M, while eta are one forms on sigma valued in the pullback of the cotangent bundle of M. So they are one forms both on sigma and on M, whereas dx are one forms on sigma valued in the pullback of the tangent M. One can work out the equations of motion. They look like that. And if one checks the compatibility of the two, namely replaces one into the other, one obtains that pi cannot be a generic antisymmetric bivector field, but it has to be Poisson, namely the Schouten bracket of pi with itself has to be 0. So this is simply another way of writing the Jacobi identity. Okay. Then if sigma is a manifold with boundary, then we need some boundary conditions for the auxiliary field eta. So you see, I call eta an auxiliary field because the action is in a first order form. And it can, we can integrate away these auxiliary fields at I only if pi is non-degenerate with inverse this symplectic form omega. Otherwise, we have to stay with this hybrid expression here. The model is invariant under diffeos of sigma. So the Hamiltonian setting. So we choose for sigma the product R times the interval 0, 1. We write eta the one form in local coordinate. Eta I is still a one form on sigma. Then the Lagrangian acquires this form here with beta and zeta being respectively the time and space component of the one form eta, and x dot x prime the derivatives with respect to time and space. So one can see from the form of the Lagrangian that minus zeta I is the conjugate variable of the field xi with canonical Poisson brackets, all others being 0. This means that we have primary constraints because there's no field b dot, beta dot. And there are also secondary constraints, this one here, which means that the Hamiltonian that one can work out is itself a pure constraint. And these are indeed first-class constraints, so they generate gauge transformations. One can check the Poisson algebra of this family of Hamiltonians, and one finds that it closes, namely one can check this equation here, provided one allows for the gauge parameters beta to be field dependent. Then the bracket that is here is an extension of the Koszul bracket for one forms on M, which is this one. Which I think we have also seen this morning in one of the talks. So this bracket here, this Koszul bracket for one forms satisfies Jacobi identity only if pi is a Poisson tensor, and this is the natural pairing between one forms and vector fields. T star M and Tm. I is the contraction, the interior product. So the map which associates to gauge parameters beta, this Hamiltonian here, is a Lie algebra homomorphism. The Hamiltonian constraints are first class, and the Hamiltonian vector fields associated with this beta generate with H beta generate gauge transformations. Okay, then C is the constrained infinite dimensional phase space of the theory. Sorry, P. P is the infinite dimensional phase space of the theory. One can quotient this space with respect to gauge transformations, and an important result due to Cattaneo and Felder is to show that the reduced phase space is indeed finite dimensional, and it has dimension twice the dimension of M. So this is in short the Poisson sigma model. Let's see the generalization that we propose for Jacobi manifolds M. So what is a Jacobi manifold? It's a manifold endowed with Jacobi brackets, which were introduced in '78 by Nerovitz on the algebra of functions on a manifold M. So these brackets are defined in terms of a bivector field and a vector field E, which is known as the Rib vector field, and the bracket acquires this form. With some compatibility conditions between lambda and E in order for the Jacobi identity to be valid. So this is the Schouten bracket, again, which tells us that lambda does not satisfy the Jacobi identity, namely it is not a Poisson bivector field. And this is the lead derivative of this bivector field with respect to E. Of course, if E is 0, then we are back with Poisson structures. So the Jacobi identity holds for this bracket here, not for lambda, as I said. And also the Leibniz rule is violated by this term here. Namely, this bracket is not a derivation for the algebra of functions on M. As I said, E equals 0 is the Poisson bracket, and there are two main families of Jacobi manifolds, which are odd dimensional examples, contact manifolds, and even dimensional examples, which are locally conformally symplectic. There are generic Jacobi manifolds which may be described in terms of foliations with contact and or locally conformally symplectic leaves. This is a result due to Weissman, I think in 2000. So a simple example that I will work out in the end is the case of SU2 as a contact manifold, and an example of locally conformally symplectic manifold that one can think of is simply the product of a contact manifold times the circle S1. One can see that this can be made into a locally conformally symplectic one. Okay, so let me say what it is a locally symplectic manifold first, and then what is a contact manifold. I base my definitions on these two works of Poisson and Marle. Locally symplectic manifolds are even dimensional manifolds with a two form, which is non-degenerate and not closed, but it is locally equivalent to a symplectic form by a conformal factor e to the minus f. So Xi would be a symplectic form. Or one can write it globally, namely d omega is not zero, but it is minus alpha wedge omega, where alpha is a one form. Once you have this two form omega and this one form alpha, you can define the Rib vector field and the bivector field lambda in this way. So the Rib vector field is implicitly defined by the contraction with the two form omega, and lambda is essentially the inverse of these two form. Okay, whereas contact manifolds are defined so that they have dimension 2n plus 1. They have a contact one form theta and a volume form, which may be obtained in terms of theta and d of theta. And again, the structure lambda e can be obtained in this way. So the contraction of the volume with E must give the theta to the n, whereas the contraction of the volume with lambda must give this this form here. In order to have an idea of what these conditions mean in a simple low dimensional example, in dimensions m equal 3, they simply mean that E has to be the inverse of the dual of theta, and lambda has to be the inverse of this d theta. We will see in the SU2 case explicitly what the structures are. So let me mention another ingredient, which is Poissonization, because it is useful to define a notion of Hamiltonian vector fields for this Jacobi bracket. So once we have a Jacobi structure, we can construct for the manifold M times R a homogeneous Poisson bracket in this way, where tau is real. Homogeneous simply meaning this. So once we have a Poisson bracket over M times R, we define a Hamiltonian vector field, which is this x pi for the function e to the tau f, which is defined in the usual way. Then we project it down to the manifold M, and this is our definition of Hamiltonian vector field for the Jacobi structure. Why is it a good definition? It is a good definition because the map which associates with F, this vector field XF that we get by projecting, is a Lie algebra homomorphism, where here we have the Jacobi bracket between functions. So we have a notion of Hamiltonian vector field, which we shall use to define the generators of gauge transformations. So once we know what is a Jacobi manifold, the proposal for an action with M as a target space is this one. Again, X is the embedding map, but now instead of having only eta, one form valued in the pullback of the cotangent bundle over M, now we need also this field here, which is needed to take into account this rib vector field. And now the structure is this one, namely eta lambda is a section of this bundle now, where J1M is the one jet bundle over M. Namely, it is simply this object here, T star M plus R. One can also think of this J1M in terms of sections in terms of these one forms. So the couple alpha F would be the section of this J1M. So we will, this is closed again with respect to the Koszul bracket on the manifold M times R. So if one writes this expression in coordinates, maybe it is more clear what it is. So this would be, this in red would be the action of the Poisson sigma model, where lambda in that case is Poisson. Now we also have this factor here, EI of X, eta I wedge lambda. Eta I and lambda are one forms over sigma. Okay, so we go again to the Hamiltonian approach because we want to perform again an analysis of constraints. So we write explicitly dx, eta, and lambda locally in this way. The Lagrangian acquires this form. This factor with EI and this factor with EI would be absent in the case of the Poisson sigma model. One thing I didn't say is how to justify this action here. Well, if one constructs the Poisson sigma model for the manifold M times R, works out the dynamics and then projects it down to M, it coincides with the dynamics that one gets from this action here. So it seems reasonable as an action. As I said, this is the Lagrangian, where lambda t and lambda u appearing here are now scalar fields, whereas x dot, x prime, beta, and zeta have extra indices on M. We have boundary conditions as in the Poisson case, but this is a boundary condition only for beta, no boundary condition for lambda, and this is the Hamiltonian. So again, we see that minus zi is the conjugate variable of xi. We have more constraints than in the other case, and we have more secondary constraints than in the other case, but they are not all on an equal footing. Some of them will be first class, some of them will be second class, which means that we have to get rid of them before talking about gauge invariance. So as I said, one can analyze the algebra of constraints and check that there are indeed there are these other constraints. The rank is not maximal, which means that we do have first class constraints, and then one can choose locally a basis for the vector fields on M in such a way that the Rib vector field only has one component. This simplifies the analysis of constraints, and one discovers that only these 4 objects, 2 primary, 2 secondary, are second class. All the other are first class. They generate gauge transformations, and I write explicitly the generator of gauge transformations here. So A now goes from 1 to M minus 1, M being related to the Rib vector field. All these are gauge parameters. And one wants to check again whether this algebra, the algebra of gauge transformations, closes or not. And we observe the same phenomenon as for the Poisson's sigma model, namely, if one wants that the algebra closes off shell, namely without using the equations of motion, then we have to allow for gauge parameters to depend on fields. And once we do this, so this means that they depend on fields. Once we do this, I rewrite my gauge generators in this way, so as a combination of constraints, and I check the brackets, and I get something which is still of the same form, namely a combination of G beta C and G lambda T, but with these coefficients. What are these coefficients? Well, these coefficients rearrange beautifully, I would say, even if it takes some time to notice it. And the bracket that appears here for the sections of my J1M is a generalization of the Kotzul bracket. This is known with many names, Gerstenaber bracket or Batalin-Bilkovitsky also. I will call it simply the Weissman bracket. And it looks like that. So the bracket of these 2 sections will give another one form and a function h, which are expressed in this way. When E is 0, you get back the Koszul bracket that we had. And this bracket here satisfies Jacobi identity if M is a Jacobi manifold. So okay, so we can summarize what we have up to this point. There are also second class constraints. We can get rid of them and look at the gauge transformations, which are generated by first class. The algebra is closed. And there are some further results. So we were able to show a result which is similar to the one obtained by Cattaneo and Felder concerning the dimension of the reduced phase space. So one can prove that given the reduced phase space C, now I am using this should be the constrained manifold, I am sorry. The subspace spanned by the Hamiltonian vector fields associated with the gauge generators has a codimension 2 times the dimension of m minus 2. This simply means that, again, if we quotient the constrained space with respect to gauge transformations, we get, again, a finite dimensional manifold with dimension twice the dimension of m, this times minus 2, because we also have second class constraints. I will not enter the proof of the theorem. Something which might be probably more interesting for the audience is that one can integrate out, in this case, the auxiliary field always. So, and for compact manifolds, what one gets is a second order action which acquires this form. So theta was the contact one form. Whereas for a locally conformally symplectic manifold, one can also integrate out the auxiliary fields, get a second order action where omega was the locally conformal symplectic to form. This is non-degenerate and non-closed. There is also a dynamical extension of the model, which looks like this. So this is a topological action that we have seen up to now. Then when one can add this factor where G is a metric on M on the target space, while star is the Hodge star on sigma. Okay, this is what I said. And one can integrate out the auxiliary fields also in this case, and one gets an action, dynamical action, which looks like this, where G and B have explicit expressions in terms of the starting metric G on the manifold M, capital G, and the bivector field lambda defining the Jacobi structure. So let me go to the example that can be worked out completely. This is the case of M equal SU2. So this is a contact manifold with this property where omega can be taken to be the left-right invariant volume over SU2, then theta can be one of the left invariant one forms on SU2, say theta 3. Then the Rib vector field is really the dual left invariant vector field of this one form that we have chosen. And also lambda is expressed in terms of the other two left invariant vector fields, y1, y2. So if we rewrite the action that I gave in the beginning in terms of the field variables for this manifold, which are now, so phi is the embedding map which associates to sigma an element in SU2, so G is an SU2 element. So this is a fancy way of writing what we know. And eta lambda is a section here as before. T star of SU2, of course, is the cotangent. So we can write this action more explicitly by identifying the tangent bundle of SU2 with SU2 times this Lie algebra, the cotangent with SU2 times the dual of its Lie algebra. And then we can write explicitly the pullback of this one form in terms of these fields, AI and JI, which are respectively time and space derivatives taken in the Morer-Cartan one form over SU2. So this is eta, and this is lambda as previously, where EI with low index and EI with upper index are dual bases in G and G star. Here I missed G star, dual algebra. Okay, so the action acquires this form now. The Hamiltonian, as before, is simply everything but this PQ dot. And again, these are the constraints. One can work out, well, we know what are the canonical brackets on the cotangent of SU2. They look like that. Ci, Jk are the structure constants of SU2. Sigma is simply what I call the EI, namely a basis for the algebra of SU2 up to a factor of 2 Pauli matrices. And coordinates, of course, they have 0 Poisson bracket. So I can perform the same analysis of constraints as before, and I get my gauge transformations. And I want to show what the second order action looks like. So I can use the equations of motion. I can replace them into the first order action, and I get this second order action here, where A and B go from 1 to 2. D theta, well, theta is the contact 1,4. Same can be done for the dynamical model, which is probably more interesting. So G would be the left-right invariant metric on SU2, and lambda is simply this object here that we derived. Then plug everything into the dynamical action that I showed you, and I get this action here, where Hij is this metric here. And this metric is interesting, is something which puzzles a little bit us, because we obtained this metric when dealing with Poisson-Lie duality for sigma models over SU2. So this metric came out as a non-degenerate metric on the dual of SU2 in the Drinfeld double decomposition. Drinfeld double of SU2, which is the Lorentz group. So it is not clear to us why this is here. This looks like a sigma model as a standard sigma model with target space SU2, but this is not the metric that we are used to see there. Maybe it is an accident, maybe it is not, we don't know. And I think I am done, so.
Sorry, maybe you said it, but I missed it. The REAP E vector here, how does it appear in the dynamical? Is it
so the REAP vector field, once I use the equations, disappears from the action, but it imposes this constraint here. So this is its residual role. It was in the first order action here. Okay, so let me come to the summary. So what we did was to investigate topological and dynamical sigma models which have Jacobi manifolds as target spaces. We performed a constraint analysis. We derived the gauge algebra, and we found this homomorphism with the algebra of one forms over a manifold M, or a generalization of it in the case of Jacobi. And we showed, well, I didn't show you, I only stated the theorem that the reduced phase space is finite dimensional. One can work out, at least in low dimensions, explicit examples of contact and locally conformally symplectic. We are looking at the case SU2 cross S1 as an example of locally conformally symplectic. It's a bit more involved, but can be done. Perspectives, as I said, we would like to look at quantization in the spirit of Cattaneo and Felder, or if you like, in the spirit of Kontsevich. And we would like to analyze the geometry of the reduced phase space. In case of the Poisson, this has been proven to be a symplectic groupoid. So in this case, we have some partial answers. And then, of course, we would like to look for applications. And I thank you for the attention. I just wanted to mention, but it's gone, that what should I do to show again the okay, that when our paper was finished, this paper by Thanassis, Chatsis, Stavrakidis, and Simeonic came out with a similar model to ours. And then recently, there is this paper by Pansea, which studies gauge transformations of the model. Okay, thank you.
Questions? Can I ask you, do you mind going back to the SU2 action?
Yeah. The dynamical one or the topological one?
Well,
this is the dynamic. Well, they are here. Both.
So, I mean, just looking at this looks a little bit like this Yang-Baxter deformation of the three-sphere. It can be, I don't know, the structures that seem to appear look fairly similar. I was just wondering if this is a connection that you have looked at. And
well, we don't know actually, because as I said, when we were looking at the dual model of sigma model over SU2, so the dual group is known to be this SB2C. This is a non-compact group. And the action contains this metric here, but of course the fields are on SB, not on SU2. So
Mhm.
I don't know.
And the other question I had, maybe it's a bit more concrete. I miss why or how you decided which dynamical, how you determined what the dynamical term that you wanted to add to the topological term was.
So the dynamical term that I add is always of this form. This is inspired by what people do for the Poisson case. So you add this thing here. So I simply choose the left-right invariant metric on SU2, and I add to my topological action, and I get the action that I showed you.
Okay, but is there some, just what are the properties of this dynamical term, or is just something that works nicely? Or?
Well, for the Poisson sigma model, this was worked out by Peter Schupp, and the reason was that he got a Polyakov action, a string sigma model with this B field here. This was mainly his motivation. Of course, one could add something else, but this seems to me the most natural thing, especially if you have a notion of invariant metric on your manifold, which is the case of Lie groups.
Well, if you say that you have the SU2 invariant metric on the dual group, it means it's invariant with respect to the dressing action of SU2 on the dual group, or what is the action of SU2 on this SB group?
Yeah. So the metric, once you write the action in terms of group field variables, you have in the case of SB, you don't have a metric which is both invariant and non-degenerate, because the group is solvable. So you can write a metric as a trace, but where you have to take the adjoint of one of the elements in order not to get a degenerate case. And then you can see that this object is invariant under adjoint action of SU2.
So probably it will be the dressing action.
Probably, because that action is obtained by a parent action over the Drinfeld group, and then probably it is a
if it is the case,
action.
then, okay. Second question, what it means, the quantization, what kind of object should be in the quantum level which would correspond to this Jacobi bracket? It should not be probably the commutator, it should be something.
Yeah, what I had in mind is that in the case of Poisson manifolds, you get this star product, this Kontsevich star product, which is a deformation of the Poisson bracket, which is its first order. So it is a quantization of Poisson brackets. So, and what Cattaneo and Felder did was to show that each order of this star product expansion is related to the quantum field theory of the Poisson sigma model.
So when you say quantization, you mean deformation quantization?
Deformation quantization, yes.
If there are no more questions, let's thank the speaker again.